Look at this. A photograph showing what our world looks like over 24 hours as seen from the moon. Now, technically, these images weren't taken from the moon, which sits about 400,000 kilometers away. They were captured by the DSCOVR satellite, roughly 1.5 million kilometers out, about 3.5 times farther than the moon. But from the moon, Earth would look something like this. Nothing unusual in these photos, just our pale blue dot, slowly spinning through the void. Now let's flip the perspective. How does the moon look from Earth? In this video, every second equals 1 day, and every second contains 24 frames, so each frame represents 1 hour. We know for a fact that the moon rotates on its own axis, completing one full spin in exactly 27.3 days. So, why can't we see it rotate? You've probably noticed this, but have you ever stopped to wonder why? Why do we always see the same face of the moon? And what's hiding on the other side? Let's take a look. With the exception of Venus and Uranus, virtually every object in our solar system, including the asteroids and the Sun itself, rotates counterclockwise when viewed using the right-hand rule. Here's what that means. Take an object like Earth, point your right thumb toward geographic north, and the direction your four fingers curl is the direction most objects in the solar system spin. West to east. The moon is no different. It rotates counterclockwise on its own axis, just like Earth. But if you go outside tonight and stare up at the moon, you won't see any of that rotation. That's why so many people assume the moon doesn't rotate at all. Think about it for a second, though. If Earth is spinning but the moon somehow isn't rotating while still orbiting Earth, it would be physically impossible for us to always see the same face. We know the moon rotates, but if it does, how does Pink Floyd's famous Dark Side of the Moon even exist? Well, here's the thing. It doesn't. Not really. We've always seen the same face of the moon, so the side we never see got nicknamed the dark side. But dark here doesn't mean lightless. Scientists use the term the same way they use dark matter or dark energy, meaning unknown, mysterious. Because until the 1960s, virtually no one had ever seen what was on the other side. That changed on November 7th, 1959, when the Soviet Union's Luna 3 probe entered lunar orbit and sent back the very first photographs of the moon's far side. Shedding light on it, not literally, but in terms of knowledge. In the years that followed, further lunar missions brought us increasingly detailed images of that hidden surface. Take a photo from Apollo 16 in 1972, for instance. The far side is clearly lit, and strikingly, it has far more craters than the side we see. The reason why is fascinating, ancient, and something we've only recently begun to fully understand. Initially, scientists thought Earth acted as a shield for the near side, blocking incoming space rocks, which would explain why the far side took more hits. But honestly, that reasoning doesn't hold up. The moon is 400,000 kilometers away, and at that absurd distance, both Earth and the moon are tiny. Here's what the Earth-Moon system actually looks like to scale. Even though Earth's radius is 3.6 times larger than the moon's, at 400,000 kilometers apart, Earth only covers about 4 square degrees of the 41,000 square degrees of sky visible from the moon. So meaningfully shielding the moon from incoming projectiles? Not possible. What actually happened goes back to the moon's formation. As the moon was forming, its near side, facing the young scorching Earth, was significantly warmer, while the far side was considerably cooler. On that cooler side, elements like aluminum and calcium condensed more rapidly and combined with silicates in the lunar soil, forming a mineral called plagioclase feldspar, which we can still find in lunar soil today. This faster cooling on the far side caused the lunar crust there to form much thicker. So meteorites hitting the far side could punch through and leave craters, while on the near side, where the crust was thinner, occasionally a large enough meteorite would break through entirely and release the basaltic lava sitting beneath the surface. That lava would spill out, flood the newly formed craters, and bury them. Which is why the near side of the moon looks blotchy rather than cratered. Those blotches are called maria, from the Latin word for sea. Though there's no water here, just ancient lava seas frozen in time. That's why the far side of the moon is so much more heavily cratered. Now that we've covered that, let's get to the main question. How does the moon show us only one face? Here's what we're working with. Both Earth and the moon are rotating, but the moon's rotation must somehow always keep the same side pointing toward us, while Earth's doesn't. There's only one scenario where this is possible, when the moon's rotation on its own axis is perfectly synchronized with its orbital period around Earth. And when you look at the numbers, that's exactly what we find. The moon takes approximately 27.3 days to complete one full rotation on its axis. And it takes exactly the same 27.3 days to complete one full orbit around Earth. That's why, no matter when you look up at the moon, you always see the same face. Although if you photograph the moon over a long enough period, you'll notice it wobbles very slightly side to side and up and down. That's because the moon's axis is tilted slightly relative to the plane of its orbit around Earth. So as it travels around us, its north and south poles gently lean toward and away from Earth. This creates what's called latitudinal libration. It's as if the moon is nodding yes. Meanwhile, its east-west wobble is called longitudinal libration, more of a slow headshake. If you're in the northern hemisphere, it looks like a yes nod. From the southern hemisphere, like Australia, it appears reversed, because we're looking at a sphere, and someone standing on one side sees the exact mirror image of someone on the other. But here's what really makes this interesting. How did this synchronization happen in the first place? What are the odds that two randomly formed celestial bodies would end up spinning at exactly the right rates to produce this? The odds are essentially zero. And they weren't always like this. When the moon first formed, it rotated at a completely different speed. Back then, if there had been intelligent life on Earth capable of looking up, they would have seen all sides of the moon. But over millions of years, something extraordinary happened. Earth's tidal forces gradually slowed the moon's rotation. As we discussed in the tidal forces episode, tides are responsible for a stunning number of phenomena. And this is one of them. Earth's gravitational pull on the moon is not uniform. It's slightly stronger on the side facing Earth. This differential pull creates tidal bulges on the moon, and because Earth was rotating faster than the moon was orbiting, these bulges were dragged slightly eastward, about 3 degrees or 12 minutes ahead. If you remember that graphic from the tidal forces video, because the forces are differential, tidal bulges form both on the side facing Earth and on the far side. And because Earth rotates faster than the moon orbits, the bulges get pulled slightly eastward. Think about what this does to Earth's rotation. The bulge closest to the moon experiences a gravitational pull from the moon, a force that, as we discussed in the "Why Does Everything Spin?" video, creates a torque acting against Earth's rotation. This is why Earth's day is getting longer by about 1.09 milliseconds every 100 years. The moon is very slowly bringing us to a halt. And just as Earth raises tides on the moon raises tides on Earth. And that's exactly what slowed the moon's rotation down. It slowed and slowed and slowed until it reached the exact speed where only one face points toward Earth. We call this final state tidal locking. And the reason it's even possible comes back to those tidal bulges and their roughly 3-degree, 12-minute eastward shift. As a side effect of this same process, called tidal acceleration, the moon is also drifting away from us. It moves about 3.8 centimeters further from Earth every year, just like an X who keeps putting distance between you. Tidal locking, the end result of tidal acceleration, isn't unique to the Earth-Moon system. Technically, every rotating object in the universe is trying to tidally lock everything around it. But in most cases, the distances are too great, the mass differences too large, or the gravitational interactions too complex for it to actually happen. In practice, we see tidal locking mostly between stars and their close orbiting planets, or between planets and their moons. And the size difference between the two objects determines which one gets locked. Because the moon is 81 times less massive than Earth, it's the moon that gets locked. Only the moon shows us one face, while from the moon you can still see all sides of Earth rotating freely. But when two orbiting bodies have roughly similar masses, both can end up locked to each other. In our solar system, the clearest example of this is the dwarf planet Pluto and its moon Charon, which is only about 9 times lighter than Pluto. Pluto always shows the same face to Charon, and Charon always shows the same face to Pluto, because the orbital period of each around the other is nearly identical to their individual rotation periods. That's how it works. What I find most powerful about stories like this is the realization that even the most ordinary things, something as familiar as glancing up at the moon, are hiding layers of breathtaking, intricate science beneath the surface. I wanted to share why the moon always shows us the same face. If you enjoyed this, leaving a like or comment means a lot. See you in the next video.